We're happy to have Professor Phiala Shanahan from MIT, and her last lecture will be about machine learning and theory calculations.
Okay, thank you. So a bit of a change of pace today from the last few lectures about fermions on the lattice. This is about machine learning and theory. Okay, so after some conversations at lunch and coffee breaks, we're going to start sort of simple and then build up. But one of the main things that I want to try to communicate through this lecture is that there's much more of a problem framing problem in using machine learning than anything else. The real question is how you set up your algorithm to use machine learning. And then you can use all of the toolkits, but the question is problem framing. And let me start with an example. Let's say I need to invert a matrix, right? And I want to do it fast and I want to use machine learning. You can do something that's a really, really bad idea. You can say, I'm going to take a neural network, and we'll talk more about what neural networks really are later. I'm going to take a neural network. I'm going to say the input is my matrix, and I want the output to be the inverse. And I'm going to optimize it based on a bunch of matrices and their inverses and try to make it as good as possible, and I'm going to use that, right? That would be a naive thing to say, okay, let's use machine learning to try to get an inverse. What's wrong with that? Anyone want to guess why that's not a good idea? Yeah. Yeah, you're going to get something that might be pretty close to an inverse in most cases that you've tested on. Maybe you say, well, on average, the error is 10 to the minus 5 or something. But you have no way of knowing how good it is on another example unless you invert it using a trusted method some other way, right? You have an uncertainty. However, that doesn't mean you can't use machine learning to get exact inverses. It just means that doing it that way is bad. What you can do instead is you can say, I'm going to use my neural network not to output the inverse of the matrix, but to output a preconditioner for matrix inversion, right? A preconditioner is a matrix that you can multiply on your matrix so that the normal inversion is faster, and then you undo it afterwards. So you're using machine learning to change your problem into one that's easier to solve using your guaranteed correct algorithm, and you have guarantees of exactness. And you've used exactly the same machine learning approach. In both cases, we've just used a neural network, right? It's just the way we're using it in one case has an uncontrolled uncertainty, and in the other, it's exact. And so that's really the underlying message of what I want to say, is that really the important thing is step one. It's framing your problem the right way. And then machine learning can be really, really powerful. But just trying to sort of blindly use it is not good. Okay. Oh, because you learn a preconditioner for the matrix inversion, right? Then you use your regular inverter on your preconditioned matrix, which should converge much, much faster. Then you unmultiply with the preconditioner, right? So you have the same guarantees of convergence that you have with whatever regular inversion algorithm you're using. So you have your exactness guarantees. So there's no uncontrolled systematic that you're introducing. So the accuracy of the inversion will be however good, whatever standard inversion method you use. Usually you use some tolerance that you can tune. Whether the preconditioner is good or not, that will depend on how well you've optimized your machine learning algorithm. If it's badly optimized, it won't get much faster. If it's well optimized, it will get a lot faster. And that's one of the key things that I'm going to come back to. But that's the overall message that I want to share, is that using machine learning for theory, step one is a problem framing problem. And step two is apply all the mechanics. Yeah. There's lots of ways of making preconditioners for matrix inversions depending on the problem. You can look up things like even-odd preconditioners if you care about lattice. There's also multi-grid preconditioners if you care about lattice things. There's Hasenbusch, there's lots of constructions you can use. But you can do better by having them be specific to each matrix you want to invert through a machine learning framework. Okay, good. So let's get started. Like I said, I promised some basics. Okay, so broad umbrella, artificial intelligence. This is the general branch of computer science that's trying to mimic human intelligence, right? That includes everything from things like ChatGPT to trying to make an actual robot that can walk around, right? This is generic branch. Then we've got machine learning. Which is a subset of AI based on statistical inference, statistical learning algorithms that you optimize. Right? Okay, and then we've got deep learning, which is a class of machine learning techniques that were basically developed to try to mimic what happens inside the human brain, where you have a whole bunch of transformations through neurons. And so deep learning is machine learning techniques where you have a series of transformations or layers that are sometimes even called neurons because of how they're inspired by the human brain, right? So this is a subset of that, it's a subset of that. So you might have heard of deep artificial neural nets, where you have a series of transformations that you're filtering data through. Okay, so you might also have heard of various categories of machine learning. I don't find them very useful, but I think it's useful to know what the words mean. So typically people talk about 3 categories of machine learning approaches, which are supervised, unsupervised, and reinforcement. I'll just define those words before we get into it too. Okay, so supervised and unsupervised and reinforcement, they're basically what they sound like. Supervised is you optimize, so we're talking now specifically about machine learning, I should say. That's this subset of artificial intelligence based on statistical optimization, right? In machine learning, supervised learning is where you start with some set of input-output pairs, and you say, I want to optimize it based on these sets, right? And so in some sense, you're supervising what it's learning by saying, here's an input, I want you to give me this output for this input. So the algorithm is optimized with a set of input pairs or data. And so an example would be, you could optimize a function to tell you whether a picture is a cat or a dog based on existing pictures of cat and dog where you have labels associated with the data, right? Unsupervised is where you optimize your algorithm without having a set of labeled data to start with. So typically, you would use this type of an approach to find similarities or differences or patterns in the data without wanting to say what those patterns are to start with. So clustering would be an example where you say, the target of my optimization is to break this data up into clusters that are similar in some way. Right, that's a different optimization target from here's a set of data and I want to build a map between them. Okay. One of the reasons I don't like these categories much is that there are certainly things where it's not clear which of these categories it should live in. If you don't start with some sort of a data set, but you generate data from your algorithm as you go, then you might have no original data set, but you also have data with labels that has come at some point of your training. And so you could argue about which category that falls into. So these are not clearly cut lines. But typically, if someone says supervised learning, they mean they're starting with some data set. Unsupervised, they mean they're not. Okay. Then reinforcement learning. This is where you optimize the algorithm through interactions with some external environment. So examples of this would be, playing a video game, right? But generically, you have a trial and error way where various actions get some feedback from the external environment, right? And then you run the algorithm for some time, then you stop, and then you run the whole thing again. And through your optimization, you've learned which actions are more likely to lead to rewards versus penalties. Okay, so this is using rewards and punishments. Okay. Any questions so far? This is really just some terminology. Okay, good. So we don't have a huge amount of time, so I really want to focus on deep learning or machine learning for theory, hence the title of the lecture, and specifically about the parts of deep learning where what you're really talking about is function optimization, right? Function optimization could be applied to any of these types of problems. You could have pairs of input and output data. You could ask your function to do some clustering task, right? But you have a highly parameterized function. You want to optimize it, and you want to use it in some theory calculation. Okay, so let's focus on function optimization for theory applications. And like I hinted at before, the question is, what do you want your function to do, right? How are you going to optimize it? How are you going to parameterize it in terms of free parameters? But most importantly, where in your algorithm is that function going to go? That's sort of tied up with the first one. What do you want your function to do? And for theory calculations, I think that last one, how do you build your function into an algorithm, is the most important part that gets often forgotten. Okay, so thinking about machine learning for theory broadly, of course, there are fantastic applications in data analysis type problems. I'm not going to talk about them, but I don't want to neglect them. So this would be things like global fits, classification, interpretation, finding structure. But I'm going to be much more focused on how you can use machine learning to do a second class of theory problems, which is to accelerate calculations where you want those calculations to be exact. Maybe those calculations are effective field theory, lattice field theory, some perturbative calculations, doesn't matter, right? Accelerate calculations where you want rigorous guarantees of exactness for your results. And the key about this is that you have to use machine learning in a way so you have no modeling, approximations, errors, systematic uncertainties, right? Otherwise, you're no longer doing a controlled theory calculation. Okay, so now I'm writing down what I really sort of said at some length at the start, is that you need to set up a scenario where if you poorly optimize your machine learning algorithm, your results are mathematically correct. And if you have a well-optimized machine learning algorithm, your results are correct. And the only difference is, hopefully, if it's well optimized, it's fast. And if it's poorly optimized, it's probably slow, right? If you're doing an integral and the value of the integral is 3, it better be 3. Whether you're using machine learning or not, you better get mathematically guaranteed to get the number 3. Just hopefully what you get out of using machine learning is that you get that it's faster. Right? There's nothing else it can do for you. There's no, you're not looking for some structure in the number 3, right? You just need to get 3 faster. And so this is really framing the problem so that you get this is, I think, the thing that's least well appreciated in setting up machine learning for theory. Okay, let me give some examples. And the problem with this is, of course, that this is not how machine learning is used in most industry applications. Because in most applications, if you're trying to mine data from people's Amazon searches, there is no correct, right? And so this is not the framework in which most big applications of machine learning are used. But just by changing how you think about the problem slightly, you can use all the same tools without sacrificing correctness. Okay. So examples. Okay, so 3 categories of examples. The first is the least interesting, but shouldn't be neglected. It's use the optimization tools of machine learning to do the calculation the same way, but faster. That means whatever the calculation is, you have some existing algorithm, and maybe that algorithm has some free parameters that you have to tune. Maybe you can tune them much more efficiently using machine learning, right? So then you're not changing it. You're still using the same algorithm. You're just maybe using it more efficiently. So that's sort of least interesting, but an important option. Okay, so I gave the example of use machine learning to tune free parameters of an existing algorithm. Or another example would be maybe you have a stochastic optimization as part of whatever your traditional algorithm is, right? The automatic differentiation toolkits in machine learning packages can be much, much more efficient than stochastic optimization processes. We've used this particular example, so use automatic differentiation instead of stochastic optimization. We've used this example to great effect in some effective field theory calculations recently. We're doing a nuclear effective theory in a finite volume. Wave functions were originally optimized using correlated Gaussians that were selected stochastically. And you can get the same level of convergence with 5 Gaussians optimized using machine learning automatic differentiation packages as you can with about 200 Gaussians optimized the traditional way. And this hadn't been done before, and it really is just literally use the same approach where you have correlated Gaussian wave functions but you're optimizing it much more efficiently using this toolkit. And in that particular example, that let us get from studying 3-body nuclei to studying 10-body nuclei, right? So small change, useful of impact, no loss of exactness guarantees. Okay, more interesting is to transform the problem. Ideally, to one that's computationally easier. With the same solution. We do this all the time, right? Changes of variables can make a problem go from really, really hard to really, really easy. Choosing the right choice of variables can really help. You can use machine learning to help you make that choice if you can't come up with a good analytic choice, and that can sometimes be incredibly efficient. So this would be, also the example I gave of preconditioning falls in this category. So e.g. any sort of preconditioning, change of variables. So last night in the discussion session, we were talking about contour deformation. That's an example of a change of variables. If you have a complex contour integration, you know that as long as you don't cross a pole, you can deform it however you like. And if you can parameterize deformations that don't cross poles, you can optimize it so that your numerical integrator has smaller variance for the deformed contour, right? And then you just have an optimization problem. It's which contour will give me the smallest variance when I try to do the integral numerically. So it's just phrasing this sort of a change of variables as a machine learning problem. So this would be contour deformation. Okay, and the last one is to solve a different problem as long as you know how to fix it. So I know I'm sort of laboring this, and this doesn't really feel like machine learning. This feels like problem framing, but I think this is one of the most important parts of using machine learning theory. Okay, so examples of this would be if you want to sample a probability distribution, you can sample a nearby probability distribution. And as long as you can actually compute the density, you can correct it using reweighting or using Metropolis-Hastings except reject steps. So that's easy. It places a requirement that you must have a sampling approach where you can compute the density. So each of these different ways of framing the problem will place some requirements on how you set up your machine learning problem. So sample nearby probability density, and then reweight. Another example would be, we do this all the time, sloppy versus high precision solves of linear systems, and then you can bias correct statistically, mathematically, you can do the same thing. So okay, and then the main point is that often framing your problem like this will place some constraints on how you need to set up your function optimization problem to start with. You'll need to enforce things like symmetries, limits, maybe you need invertibility, maybe you need a Jacobian of a transformation to be computable, and that will constrain the way in which you're able to do machine learned function optimization. Okay. Any questions? Yeah, certainly. Yeah, there's no conflict between 1 and 2. I'm just focusing on 2 because for number 1, that I'm broadly classing as data analysis, that's much closer to the way in which machine learning is used in many other applications, right? Like if you're trying to take images from a telescope and identify some structures automatically through a machine learning algorithm, that's really similar to trying to find faces in images of, you know, in images like Google's doing it. So you can much more take something that's already been developed off the shelf and apply it. Whereas if you need to build in exactness, that doesn't really exist in many other venues other than science, maths applications. So it requires a bit more problem framing effort. That's why I'm focusing on it. Yeah. Yeah. Yeah.
The nice idea I guess is like, for instance, by frame this no then that input is what leads to develop the potential variables that are going to be forever.
So that would be one way of doing it. There you're trying to frame this as a supervised learning problem, right? You're trying to say, I have some examples and I want to generate others. But more generally, you could frame it as an unsupervised learning problem where you say, my goal is to minimize the variance. And then what you're minimizing has nothing to do with any examples of other variable transformations. You're saying, let's parameterize a general variable transformation and optimize it to minimize the variance. So each of these you can phrase as sort of any of those types of problems. Yeah. Okay. So how many people here know how neural networks get optimized? Okay. Not so many. Okay, so let's talk about neural networks. We'll talk about artificial neural networks and then talk about how you can write down versions for more interesting science cases. Hopefully we'll have time. I'd like to get to say, let's have an artificial neural network like the standard case would operate on real numbers and map them to other real numbers, right? But what if your data lives on a compact connected manifold that's not like the real line? Even just a circle, right? You can't just take the real line and wrap it around. You have instabilities at the endpoints. You won't be able to optimize things. So how would you write down neural networks for compact manifolds? So I'm hoping that's where we'll get. So examples of how you take these ideas and apply them to more interesting cases for physics. And if we have time, I doubt we'll get there, but we could talk about gauge symmetries and how you can get those into machine learning algorithms. Okay, so neural networks. Are functions with a lot of free parameters to optimize, and they're functions that can be computed very efficiently. Neural networks have been around for a really long time. What really made breakthroughs was being able to stack many, many layers of transformations to make them deep, and the way of optimizing them through what's called back propagation. It's basically the chain rule. Okay, so everything that I was talking about in the framing, I was talking about function optimization, right? Like here, your function would give you the parameters of your existing algorithm, right? Here, the function would give you the steps to take when optimizing your parameters. Here, your function would give you a preconditioner. Here, your function would give you the change of variables, right? In all cases, there's a function that you want to optimize, and one of the useful basis components for those functions in neural networks, which are functions with many free parameters that can be efficiently iteratively optimized. Okay, So you take some sort of input of a fixed dimension and it gets transformed to output of a fixed dimension. You can generalize these in more interesting ways, but the basic thing is just fixed dimension input to fixed dimension output. And it's structured as a whole bunch of matrix multiplications and nonlinear transformations. And that's why you can put it so efficiently on especially things like GPUs. Okay, and people speak a lot about the universal approximation theorem, which says that a sufficiently general neural network can approximate any sufficiently smooth function. That's nice. It's not really a practically useful fact if you're trying to use a neural network to do some physics calculation. So in particular, what I mean by that is it's a misconception that that fact means that if you keep making your neural network bigger and bigger and train it for the same problem, that it will converge to the right thing. That is not true, right? It is true that a sufficiently general neural network can represent any function in a certain class. It is not true that taking a series of neural networks and optimizing them gives you some sort of convergence to that point, right? And that's a sort of common misconception. People think that they have a, completely general function approximation. Hey, audio guy, are you waving at me or are you just stretching? Okay, cool, sorry. Awesome, right, so common misconception that it doesn't prove anything to train a series of neural networks and see that you keep getting the same result, right? So you have to be aware of this. I'm going to write it down because it's important. Universal approximation theorem says that a sufficiently general, and I'm actually going to write down what a neural network is as well. A sufficiently general artificial neural network can represent any continuous function of input data to any desired precision. And I want to emphasize that this does not mean that training a sequence of increasingly large ANNs on some data has some interpretation. Just a second, can't you? Interpretation in most cases. Oh, okay, yeah, I'm sorry. You need me to write this again, or if I read it, is that okay? This says, does not mean that training a sequence of increasingly large artificial neural networks on some data has an interpretation in most cases, right? Is this statement clear to everyone, or are there questions on this? Sort of important, so I'm happy to talk about it. Yes. The problem is that you have a highly complicated system right? Imagine you have a function with an absurdly large number of free parameters, think billions, right? What that optimizes to depends on a lot of factors, and there's an interplay between the expressivity of the function, like the theoretical best possible optimized value, and the training dynamics of how you optimize. So the endpoint can depend really sensitively on the initialization of all of those parameters. Typically, you set them, all the parameters at the start, to some random values. And where you end up optimizing to depends on what loss function, I was talking about loss functions in a minute, but what optimization target you're using, what the function is that you're optimizing to, how you initialize your parameters, how you initialize your optimizer, what sort of an optimizer you use. It's not the case that even with the same neural network on the same data that you'll train to the same point. And so that's why you can't say that the universal approximation theorem means if I keep making it bigger, I'm going to converge, right? Because there's a lot of other factors at play there. And certainly when you get to these really big networks, they seem to be much more sensitive to how you've optimized them than how flexible the parameterization actually is. So it's saying much more about your optimization process than about the actual flexibility of the parameterization. Yeah. Anything else? Yeah.
You said there is a neural network that approximates pretty well, but we cannot do our training to by this company.
Not quite. The first one, the universal approximation theorem, says that in the limit of an infinitely big neural network, where big is defined in the right way, you can approximate any function. That does not mean that in practice, optimizing that, you will approximate any function. It just means that theoretically you have the capacity to.
Yeah, so there is a possibility that we can optimize actually.
Yes. For sufficiently large, it is a possibility, but it's not at all guaranteed in practice that you'll reach that theoretical maximum. Yeah. For sufficiently simple systems, yes, people make a lot of efforts on this, and there's some nice things you can prove for infinite width neural networks about the depth and so on. But in practical examples, no, because typically the problems where you want to use these sorts of techniques are sufficiently complicated that you're way outside all of the assumptions you have to make to try to prove anything. Okay, so let's write down what a neural network actually looks like and how it's optimized. It's so easy to just use a package and type in neural network, .optimize, that it's easy not to know exactly what it's actually doing. Okay, so simple neural network. And of course, as soon as you start having to put various constraints on your structures, things like symmetries, invariances, invertibility, you really have to care about what's happening under the hood, right? So it gets more and more important. Let's have one input, two outputs. The neural network diagrams that you see look something like this. Right, people usually draw these dots with lines on them. What that means here, this represents the input. This represents the output. This represents some hidden units or neurons. Okay, but what this, and so this would be one hidden layer with two neurons. Okay, what this actually is doing is X here is some number, right? Everything's based on matrix multiplication, so you never process just one input at a time. So we can write x as a vector, right? So this is x, and we'll call it a 1 times n vector, where we're going to process n samples at once, and x just a single dimensional input, right? So that's the 1 times n. These two lines here, they represent weights. Those are free parameters. So this is a weight, this is another weight. And what's happening is this is just taking a dot product with these weights that are free parameters. So these are okay. And then the dot product of this input with this output, of course, gives me a 2 by n matrix. Right? Typically, at this point, you add a shift. You shift this with what's called biases. So those are additional free parameters that you don't see in the diagram, but they're implicitly there. So these are biases. And then typically you take this input, this plus the shift. And so the shift is applying the same shift to each of these n pairs, right? Typically, this matrix then gets put inside some nonlinear function. I'm going to write this in maths expression in a moment as well, if the diagrams are getting confusing. So this is some nonlinear function. Okay, so this has now got us to the point, this is a 2 by n matrix. This is H. That's this. So H1 and H2 represent these two numbers that we got by starting with our input, taking the dot product with the weights represented by the lines, shifting with some offset. And then we have for each of our n samples, 2 numbers, which are these 2. That's what 2 neurons means. It means at this stage of the calculation, each sample of 1 number is now 2 numbers. Right? Okay. Then there's one more line. We go from here to there. You see there's 4 lines there. There's going to be 4 weights that go with that transformation. So this will be a dot product with weights W0. So this is W01, W02, W0. I drew 1, 2, 3, 4. Yeah, W03. Okay. That dot product gives us another matrix. We add biases again. That gives us another matrix. And we apply another nonlinear activation function. Then we're left with this output is y. It's 2, because there's 2 outputs y here. And that's all that's happening. Matrix multiplication, nonlinear activation function. And from the diagram, you can see the weights. You can't see the biases, so you only explicitly see some of the free parameters from the picture. I'm going to write a maths expression for this. Yeah. So okay, so f of x can be written like this. Okay, where sigma 0 and sigma h, those are some nonlinear functions. The WH, the W0, the BH, and the B0 are the free parameters. And when you train or you optimize a neural network, you're optimizing the parameters living inside those guys. It's a choice. right? It's a hyperparameter, if you like, defining the network architecture in the same way as the number of layers and the number of neurons. I write down some examples in a moment of nonlinear functions. You might have some reason for choosing one. For example, you might choose a nonlinear function that gives you output in the range 0 to 1. If you want your answer to be in the range 0 to 1, you can use the nonlinear function to achieve that. But it might just be some nonlinearity, right? Okay. Any questions about that? How many free parameters are in this neural network? Huh? 10, right? We can count them. There's 2 in the first set of weights, 2 in the first set of biases, 4 in the next set of weights, and 2 in the next set of biases. This has 10 free parameters. And if you want to make it deeper or have more neurons, right, you can imagine how that number of free parameters goes up. And then imagine how deep you need to make it and how wide to get a billion parameters, right? And you can see why this optimizing this function is such a sort of horrific task. Okay. Any questions? Yeah, I'll say in a moment about how this is actually optimized, but for now, question about activation functions, I can give you some examples. So these activation functions, right, they're the only thing that make this not just linear. Otherwise, it's just matrix multiplication. So if you want to be able to represent some arbitrary function, they're important. You can choose anything you like, but you'd like them to be nonlinear, differentiable. You might like them to be monotonic or smooth. It depends on your application. Choice depends on the problem. Okay, so popular choices. Okay, so this is called a ReLU, rectified linear unit. It's not smooth. It's just 0 to the left and x to the right. You could have, the log of 1 plus e to the x. You could have what's called an LU, exponential linear unit. Really doesn't matter, right? Just something nonlinear. Sometimes one will work better than another for a problem. This is sort of a trial and error mostly, unless you want something that has a specific property like tan, where you constrain your output to some range. Okay. Once you have it, you've defined a function. It's got a lot of free parameters. You have to optimize it, right? Okay, and the lingo for the optimization target is loss function. It just means what is the thing that you're minimizing in order to optimize all the parameters in this big function. So once you've defined it, the free parameters are optimized to some target. and you have to minimize a differentiable loss function. So the differentiable part is important for how the minimization is done, but you can write down anything differentiable. It doesn't have to be exactly differentiable. You might need to write down a numerical approximation to it. It doesn't matter, as long as it's in some sense differentiable, you can use it as a loss function. So if you had input-output pairs, that's only one of the types of classes we talked about. But if we had input-output pairs and we want fx to be like y, we're going to minimize a loss function, which will be some function of fx and y. And you can choose this to be anything you like, as long as the minimum is where you want it. So an L2 loss you could use an L1 loss. You could use a Posh loss. Huh? Oh, it doesn't have to be. Typically, yeah. I mean, it really doesn't matter. As long as the minimum of this is where fx equals y, you can choose anything you want. You also don't have to take a choice and then stick to it. You might find that taking one choice early in training and then another choice later helps, because maybe you want to think about having a really, really high dimensional landscape, loss landscape that you're moving in, right? And so this is a one-dimensional version of it, but you have some high dimensional landscape, and what your loss function is will change what that landscape looks like. And you're trying to find the global minimum, right? Which I should have drawn this axis down here. Probably that global minimum is not at 0, because probably your function cannot perfectly parameterize whatever it is that you're trying to do. But the loss function helps define the landscape. Some loss functions might be, give you something that's much more peaky but flat outside of the region. So if you start optimizing with this loss function too early, you'll just be walking around never able to converge. But if you go here later, you might have a really efficient path to the minimum. Whereas here, maybe you'll get stuck in one of these false minima earlier. So it's just the coupled, it's the coupling of the loss function, how you optimize, and what the parameterization of the data is. And you can change this as you go. Yeah. Yeah. It depends on the problem. I didn't write it because it's less easy to be general, but maybe you have some definition of what you mean by clustering, right? And so you want to transform your data so that every point is close to another point. And then you minimize the distance, the distance to the nearest point, the average of that. Or maybe you have some other, it's whatever that you want your function to do. You have to somehow write it as a function that's differentiable. It depends on the problem. Yeah. It affects a lot of things. There's often papers in the machine learning community where for the large models, the benchmark models and benchmark data sets, someone comes up with a new initialization that works well for that benchmark model and data. The more unusual the problem you're trying to do, the more it is trial and error. Typically, the free parameters are drawn from some Gaussians near 0 or some variation of that. But so for a lot of the applications my group's doing, it's really, really helpful to optimize the function so that it's close to the identity to start with. And so then you initialize everything so that it's almost the identity with a bit of randomness in it and move from there. Sometimes physics intuition can be really helpful. Yeah. Anyone else? Yeah. yeah, we're going to talk about that now. Okay, so back propagation, that's how you do function minimization. And it is really, the simplest thing. Okay, so back propagation. Okay, so the weights and biases are optimized just using gradient descent, basically, on the loss function. And so that means you change the weights and biases in the direction of steepest descent of the loss function. That's what that means, right? So people call it training, but it's really just optimization, right? The weights and biases are optimized by a gradient descent That's why the loss function has to be differentiable. Okay, so that means at each step of optimization, we're going to change the weights by some amount that's going to be proportional to the derivative of the loss with respect to the weight, right? And that's it. You might hear when you're training a machine learning algorithm, there's usually a learning rate, right? A parameter that sets how quickly you optimize. That's just the constant of proportionality out the front. It's how much do I step in the direction of steepest descent of the loss function every time I do an optimization step. And you compute these gradients, yeah? Yep. Big problem. Happens. In practice, so in practice, for each optimization step, you're going to use some batch of data. So not all of the data, some set of data to compute this. And you have fluctuations between the batches of data. So you do have some randomness, some stochasticity in the process, which can help to bump you out of those local minima. You can have larger steps here also, larger learning rates help you bump you out of local minima. But ultimately, I think most fully optimized networks are in some local minimum and not the global minimum of their architecture. That's sort of what we were talking about before about training dynamics versus the expressivity, the flexibility, the parameterization. At some point, you are going to be in some local minimum because in a billion parameter space, you're not going to be able to get into the global minimum unless you have very specific constraints and conditions in general. Yeah. Yeah.
So I think the other mentor is like
well, ideally, you want to define your loss function well, right? Going to be right. You want to define your loss function so the minimum is at the point you're looking for. But yeah, if you write down a loss function that has some minimum that's not the one you're looking for, you can go there. Okay, so this looks straightforward. The reason this is now so efficient is what are called auto gradient engines, which are in all of the standard machine learning toolkits, which basically do the chain rule really, really efficiently by building a graph of all of the intermediate results, and then you can wrap it up to do the chain rule. So obviously, if I want to compute the L by dW, I can write down what that is using the chain rule, right? Am I going to do that? So you basically start by changing the weights and biases closest to the output, if you like, and then just work backwards, hence back propagation, updating them all as you go. Okay, so the gradients are computed. via what's called backprop. And this backprop is just the fancy name for the chain rule. So you start with weights and biases closest to the output, work backwards. Okay, so we can start with the example that we had before, right? And for the first one, I'm going to write the indices on it. For the second time, I'm going to ignore the indices, and you can do it as an exercise because keeping track of the indices is a bit of a pain. But let's be careful for one. Okay, so this was our so this was the expression we had before. Yellow is visible, right? The other color wasn't. No objections to yellow. Okay, so these guys are element-wise, right? These nonlinear functions. Right? This X, that's a matrix, right? So I'm going to write I, K, K, L, I, L, L, J, I, J, I, J. Okay, so I've made the matrix indices all really explicit here. And then just the chain rule, we start with the weights closest to the output, so the W zeros, right? We're going to start with Y and then work into this nested function, right? There's layers of brackets because it's really a nested function. We're going to work from the outside in. So I want to take delta W naught, and we're going to go AB, right? This is going to be proportional to minus delta dl by dy, dy by dw naught. Right, just chain rule, that's it. And again, this constant of proportionality is just going to be the learning rate. So you choose some step size. Right? This looks like be very careful about our indices. It started as IJ, but it became an IB from the delta LA delta JB, because this had LJ, but I did d by dw naught AB, right? So the delta LA delta JB, which is why that J turned to a B. And that's it. So you'll notice a few things. We have the derivative of the loss function with respect to Y. That's why it has to be differentiable. We have a derivative of our nonlinear activation function. That's why you want that to be differentiable, right? And that's it. If we then go to the biases are easy. The next lot of weights, it starts to get really ugly. I'll write it down, but I won't write out the indices. But you just work back, no matter how many layers you have, one by one, and make changes to the weights. You could also, if you like, have free parameters inside the nonlinear activation functions. Then you just have to do the same thing, right? So define what I wanted to call XH. I'm going to call this thing. Okay, so didn't write out any indices. So what all those dots mean is quite cryptic there, but you can just do exactly this process, right? You just have to keep track. And similarly for the biases, and that's it, right? So it really is function, bunch of matrix multiplications and nonlinear parameters, change all of the weights by doing gradient descent on whatever you've said your target is. And you do that by the chain rule working backwards. And the reason this is so efficient these days is what's called the auto gradient engine, which is what's implemented in things like PyTorch or TensorFlow, which is really efficient at this sequence of operations. Because as you can see, there's lots of intermediate pieces here, right? And if you imagine you have many, many more layers, there's always lots of sub-expressions that get reused. And so this builds a graph, making this back propagation, saving all of the sub-expressions. That's why it takes a lot of memory, and then wraps them all up very efficiently to do all of these updates to this very large number of free parameters. Yeah, that's just the chain rule. Any questions? Yeah.
Where does this
You mean the optimization part, the gradient descent? Oh, well, you just want a very highly parameterized function with a lot of free parameters. And then you want it to be something that you can compute really, really efficiently for very, very many free parameters, which says matrix multiplication, basically, right? But actually, these days, these auto gradient engines, they're pretty good, and you don't have to have a function like this. So a lot of the time when you want to do something a bit more specialized, so one of the gauge equivariant neural networks that we've developed for applications in lattice field theory, the function actually involves eigen decompositions of a large number of SU3 matrices, transformations on the eigenvalues, and then eigen recompositions inside the neural network. So it doesn't look like this. But you can still optimize all of the free parameters of that transformation in the same way. This is just very efficient and convenient. And so most places, most machine learning architectures will have this sort of a structure sitting inside there somewhere. In our case, it's sitting inside special parameterizations on compact manifolds inside parameterizing the free parameters of those transformations, which are defined differently. We have standard neural networks whose outputs are the free parameters of our more constrained transformation. So inside, n different layers of structure, these come back again because they're just such efficient ways of having a very flexible function. Yeah.
For example, the structure of neural network?
Well, originally, the reason they're called neural networks is that they were motivated by the idea of neurons in the brain having multiple layers of transformations. So there's a connection there to sort of biological systems, but yes, a lot of it now is by what you can put efficiently on GPUs. Yeah. Okay. Do we have 5 minutes still, or what's the? Okay, so if you want to set up a network like this, we talked about you have to frame the problem, then you have to write down what the function is. There's a lot of truth. Oh, yeah. Yeah. Certainly, and it's very typical to start with it large and make it smaller and smaller as you imagine you're getting deeper and deeper into the well. You don't want to jump out of it by taking too big a step, and you want to not have too much noise, so you get stuck high in the well. You want to be able to slowly walk down to the bottom. So typically you might start large and make small. Sometimes also oscillating this learning rate can help get you out of local minima. But yes, typically it's changed during training. Yes, very much so. Yeah, all of these things, that's why you really want to set it up so that you have guarantees of exactness to start with, because there are so many choices that go into it. Who's to say making a different choice you would have got a different result? You certainly would have. There's no way you can explore that space fully. So there's the connectivity. You don't have, this is fully connected. Every node is connected to every other. It doesn't have to do that. And for some reason, it might be efficient not to. Convolutional neural networks essentially have a different pattern of connectivity there that focuses on local areas. The number of neurons in the layers, the activation functions, the initializations of the weights and biases, the loss function, the number of data points you use for each step of the optimization, the learning rate, the optimizer. Do you use atom optimizer? Do you use something more basic, a higher order optimizer? What's the regularization? Do you decay the weights? Do you say the weights can't be, do you clip them? Do you say no weight's allowed to be bigger than some number? All choices that will affect what the answer you get from a given architecture. Yeah. So using all the components of deep learning, the question then, how do you define the appropriate function? Your problem. Since I think I have like 2 minutes, we don't have time to go into detail, but let me give you a hint of something a bit more interesting. Okay, so we don't have time to really talk about it, but yesterday in the discussion session, we talked a little bit about normalizing flows, which is where you use machine learning and neural networks to parameterize a transformation that's a diffeomorphism, so an invertible function, so that both the function and the inverse are smooth and differentiable, right? So under certain conditions, you can write down, parameterize that in terms of neural networks, and that can be used to accelerate sampling problems, for example. It's very, very useful in that context. But if the manifolds you're mapping between are not diffeomorphic to Rn, you can't just use this sort of a construction, right? Any projection onto a standard deep learning construction will contain singularities. So that's points where you have a non-invertible Jacobian. You'll have numerical instabilities. Doesn't work. So 5-minute example is transformations on a circle. And actually what I'm writing down works recursively for spheres, tori, any dimension, doesn't matter. Just one example would be to write down a Mobius transformation. So here's our circle. Here is some number z, and I want to map that number z to a different number, parameterized by something. I could parameterize the transformation by some point omega. I can draw a line through omega back through the center, and this will be the output, the transformation of z parameterized by omega. Simple transformation, there's just one free parameter, right? So we could write that down also like this. Right, but that's sort of the easier way to visualize it. What you can do to make this more flexible is you can take omega to be the output of a neural network like this. Right, so it's a transformation directly on the circle, natively on the circle, but you make it more flexible. And then you can make it more general still. You can say, let's take if I can write down one transformation like this, maybe I can write down more general transformations like this. And you can stack them. So you can take convex combinations of transformations and you get a more general parameterization again. So this is an example where we have a transformation that lives natively on a circle. You have a lot of free parameters because they're living inside regular neural networks, but those regular neural networks are not transforming your data. They're giving you the free parameters of these transformations. Doing this, actually, it's no longer analytically invertible, but it is invertible by a bisection search numerically. So you still have all the properties you need. This is just one example. You can write down circular splines, non-compact projections, but this is an example of frame the problem so that you're not breaking it by trying to say, well, let's write the circle as a real line and put it back and deal with instabilities. You're just defining what you mean by function optimization for the problem at hand. Okay. Thanks. Any questions?
Great talk. Questions?
I'm not sure I understand this last point. The idea is we want Z to be some real number. And when we apply some transformation, so then it looks like it's a variable in the circle.
No, so in this case, I'm starting with Z that natively lives on a circle. Imagine whatever calculation you're doing has numbers that live on the unit circle. And you don't want to live on the real line. Right? And so you want to write down a transformation that lives on the unit circle. And this is one example where you parameterize the transformation by omega and map Z to a different number on the unit circle. So it's just this construction maps real numbers to real numbers. What if you don't want that? And so this was my example of, for example, if you live on a circle, you can use it in this way.
An example of the motivation function then. Is this H of Z, is this an example of activation function?
No, this is an example of the transformation of your neural network. Your overall neural network would be called this, either this F or this H of Z. So this F is just a sum of a bunch of these H of Zs. So my neural network is this overall H of Z. And my neural network takes as input a number on the unit circle, and it gives me as output a number on the unit circle. Right? It just doesn't look quite like the normal neural networks that live on the real line because we have to make sure it stays on the unit circle. So I write down this complicated looking function, but the omegas inside there are secretly regular neural networks.
And sorry, and what you were trying to optimize in this problem?
Oh, I didn't say that. One example would be that you want to sample from a particular probability distribution that lives on the circle. And then you might want a function that transforms one probability distribution to another. And you would optimize with this with a loss function that could be something like a Kullback-Leibler divergence between your probability distributions. That would be an example, but this is just a transformation on a circle.
If you just want to stay on the unit circle, why just you parameterize it by the angle theta? Is it because of some redundancies in theta?
Because that doesn't have, it's not a very flexible parameterization, right? I could parameterize it by theta, but I'd want theta to be the output of a very complicated function because I want it to be dependent on maybe a lot of information, right? So then I would have to write a neural network with lots of free parameters whose output is theta, but the output of a neural network is a real number, not an angular variable. Which takes you back to writing down something like this, where your output is something that's natively on a circle. You don't want to try to do something like wrap around, that, like say, okay, 0 to 2 pi, but then I'm going to wrap, because then you'll have instabilities in your optimization, because when you hit that endpoint, so you don't want any singularities like that.
The gauge covariance, is that mapping the gauge configurations to fundamental plaquettes?
You can do something more general. You can avoid having to use gauge invariant objects like plaquettes by, I sort of hinted at stepping via eigen decompositions. Can tell you about it later, it's sort of complicated, but I can write it down.
Any more questions? Well,
again.